9.3, the integral test and p-series. In the last lesson, we explored methods for finding the exact sum of geometric and telescoping series. In the next several lessons, we want to focus our efforts on whether or not a series converges to a sum and not necessarily find the value of the sum. So focus our efforts on whether or not a series converges to a sum, not necessarily find the value of the sum. So sometimes when we're using a test for convergence, it might equal something that makes it such that it converges. That might not be the value of the sum of that series. So we're just going to focus on whether it converges or not. The convergence tests that follow apply to series with positive terms. So far, we have seen two tests. They are stated again here. A geometric series is in the form, so geometric series test is the first one. A geometric series is in the form summation from n equals 0 to infinity, a times r to the n, which is the most common, or summation n equals 1 to infinity, a times r to the n minus 1, that's the second most common, or this third one I don't see very often. I would like to talk about it. Summation n equals 1 to infinity, a times r to the n plus 1. And I'm going to keep reading here and show you why I have a little bit of trouble with that third one. A does not equal 0, where a is the first term of the series and r is the common ratio. So let's go ahead and look at each one of these. If I put 0 in, my first term for this first one is a, right? A times r to the 0, that's a, okay? If I put a 1 in here, my first term, again, is a times r to the 0. So it holds true for those first two. But if I put a 1 into this last one, look what we get. Our first term is actually a times r to the second. Our second term would be a times r to the third. So if we were trying to say, that our a was our first term, it's actually our a times r squared for this third way to look at a geometric series. So then this would be, a times r, right? If this one is a, supposedly, then this one would be the a times r. That is the way that I think is the best to think of this. But when it's defined this way, you just need to be careful that that is your first term, okay? But you could still look at it as a times r to the 0, then your a sub 1 would be this a times r squared, right? So you could make that your a times r squared. It just would not follow with the definition that we have here, okay? So this one does not hold true for that third one, as you can see right here. This little a right here is not the first term for this summation, okay? So be careful with that when it is defined with the n plus 1, okay? There might be a reason why they do that, but you can always write it as a times r to the n minus 1 by adjusting it. The geometric series diverges if the absolute value of r is greater than or equal to 1. And so if the absolute value of r is between 0 and 1, the series converges to the sum, s equals a over 1 minus r. So if we have a geometric series, we can always find whether it converges or diverges by figuring out what r is, and we can always find what the sum of the series is, because we have this formula for the sum of the series. We also learned about something called the nth term test for divergence. And remember, this is for series, right? This is only for series, and it's a test for divergence. So the reason why this gets confusing is because they're asking you whether a series diverges, which is summation, a sub n, and you're using the sequence, the limit of the sequence. So remember that a sub n is your sequence, right? But when you put the summation on it, it becomes a series. So you're still looking at the limit as n goes to infinity of this sequence. And for this test, if you're trying to find out whether the series diverges, if it does not equal 0, that means that the series diverges, okay? So I think this is one thing that is really, really, really confusing for students every year. All right, example number 1. Determine whether the following series converges or diverges. And so we've got summation from n equals 1 to infinity, 4 to the n over 5 to the n minus 1. I'm looking at this and I'm seeing geometric series, but I would like to adjust it so that I can tell whether my r is, between 0 and 1 or greater than 1, so I can find out whether it converges or diverges. And so what I would do is over to the side, just kind of think about what this would be equivalent to. And it would be equivalent to that. If I pulled that 1/5 out in front, Henry, stop. I would have 1/5 times 4/5 to the n. And then I would think, well, I really like, since it's n equals 1 to infinity, I would really like to have this something times 4/5 to the n minus 1. So I could see what that first term is, so that if I needed to find my sum, I would have my first term. It's easy to do that. We are just basically pulling out a 4/5, right? So we're pulling out a 4/5, making this 4/25. And that still equals what you started with, okay? So you can easily see now that your first term is going to be 4/25 and that your r is going to be 4/5. So to me, this is the best way to look at this. It might be, you might be able to see it a little bit better on your own, or just even put the 1 in and see what that first term is without doing this. But I like to show kids how to do the a times r to the n minus 1 when we have a summation from n equals 1 to infinity. All right, so now you can easily see that your r is 4/5, which is, 4/5 is between 0 and 1. So therefore, this converges. It's a geometric series that converges, and its sum is going to be a, which is the first term, over 1 minus r. So we've got 4/25 times, and then this would be 1/5, division by 1/5, multiplication by 5 over 1. Divide by 5, I get 1. Divide by 5, I get 5. The sum of this is 4/5. So it converges to a sum of 4/5. All right. So now, the next one, this one, I do not see geometric series on this one, okay? What I do see, though, is, remember how we would have a ratio and we could say, well, the +3 doesn't really matter, and I can just look at 5n squared over 2n squared and look at that limit, because I want to see what the limit of my, using that nth term test for divergence, I would like to see what the limit of my a sub n is. Remember, if it doesn't equal 0, then my series is going to diverge. So when I look at this and I say, here's another way to look at it, you can take and say, I'm going to divide everything by n squared. Divide by n squared, divide by n squared. And that's going to give me the limit as n goes to infinity of 5 plus 3 over n squared divided by 2. And then this one's going to go to 0. So I'm going to get 5/2, which is not 0, right? And so by the nth term test, for divergence, the series summation n equals 1 to infinity 5n squared plus 3 over 2n squared diverges. Okay, so this one diverges. Okay, so while looking at the first few terms of a sequence of partial sums helped us with geometric and telescoping series, we will see many cases where this won't help. That means you will need to be skilled at using all of these tests to determine convergence or divergence. The remainder of the chapter will cover each of these tests. So what I did right down here is, as we're going, I'm going to remind myself, okay, well, I know how to find whether it converges for a geometric series. I'm going to look to see what my R is. My R is going to tell me whether it converges or diverges. If my R is greater than 1, I know I have a divergent geometric series. If my R is between 0 and 1, then I have a convergent series. Then we talked about the nth term test for divergence. And that one, I just put myself a little note. We're always going to take the limit as n goes to infinity of that sequence, right? But since we're trying to find whether a series diverges, okay, you're going to take that and you're going to say, if it does not equal 0, then summation a sub n diverges. Okay, if it does equal 0, we don't know. It may or may not diverge. And so integral test is what we're going to do next. So we'll come back and we'll remind ourselves what this is, what the integral test, like what we can remember about the integral test to help us, because you're going to have to, these are like the most important tests. All of these tests are the most important. So you're going to have to learn all of them for this AP exam, because I don't know which one you're going to have to use. I'm hoping that this isn't on it, but it sounds like it might be. All right, so now we're going to go to the next one. We've got exploring the integral of a series. So the integral test allows us to compare a series to its integral in order to prove convergence or divergence. Let's explore the idea by completing the table below for 1 over x squared. So if I put a 1 in, I'm going to get 1. If I put a 2 in, I'm going to get 1/4. If I put a 3 in, I'm going to get 1/9. If I put a 4 in, I'm going to get 1/16. And if I put a 5 in, I'm going to get 1/25. Okay, and they've got it graphed here. So draw the right-hand sum with 4 partitions over the interval from 1 to 5. So I know that, you've got at 1, and I'm just going to kind of draw here what my rectangles would look like. They want me to do an RAM, so a right sum. So for this first rectangle, I'm going to go to the right and then go like that, and I'm talking about this area. Go to the right and straight over, you're talking about this area. Go to the right, straight over, you're talking about that area. Go to the right, straight over, you're talking about that area. Okay, so now draw the right-hand sum with 4 partitions, find the value. Okay, so we have to remember that this is going to be our 1/4, right? So this is our 0.25, but it's 1/4. So we've got 1/4 times 1, right? So this is 1/4 times 1. So this value is going to be 1/4 times 1. So it's 1/4 for that square rectangle. This one at 3 is going to be 1/9. So when I add that, I have 1/9. This one is going to be 1/16, and this one's going to be 1/25. Okay, so plus 1/9 plus 1/16 plus 1/25, and if we added those up, approximately 0.464. Okay, And so now, find the fifth partial sum of summation from n equals 1 to infinity of 1 over n squared. So for this one, our fifth partial sum, we're going to say if I put a 1 in, I get 1. If I put a 2 in, I get 1/4. If I put a 3 in, I get 1/9. If I put a 4 in, I get 1/16. If I put a 5 in, I get 1/25. And so my fifth partial sum is going to be approximately 1.464. And then for number 3, they want us to actually take the integral. Notice for a second here, I'm going to find a different color, something light, I don't know, how about green? Notice that what we basically just found here was our LRAM. Did you notice that or not? Because if I looked at this and I did the left-hand side instead of the right-hand side, I would have gotten 1 times 1, right? If I did the left-hand side instead of the right-hand side, I would have gotten here, and I'm talking about, you know, this whole thing here, blah, blah, there, and including that, this would have been 1/4. This one would have been 1/9. This one would have been 1/16, right? So when you find that fifth partial sum, you actually took it one more over when we did the fifth partial sum, right? Because we start at 1. So, you know, and this one would have been, you know, the 1/25th. But you still are, this one is your, you know, like your lower bound of the actual integral. Okay, so you're going to think of this as the lower bound of the actual integral from, I guess I'll do 1 to 5, 1 over x squared dx. This one is like your upper bound, although you wouldn't have included this last one. You would have just had your, you know, these first 4. But that one is like your upper bound of integral from 1 to 5, 1 over x squared dx. And I guess, you know, minus the 1/25th. So, and we know that just because we know our RAM and LRAM, right? So it was almost like LRAM, right? It was LRAM except for 1 extra. But you can kind of see what we're doing here is we're trying to prove why the integral test works. So now let's actually take our integral. And so if I was integrating this one, I would have from 1 to 5 x to the negative 2 dx, and that would give me x to the negative 1 divided by negative 1 from 1 to 5. So negative 1 over x from 1 to 5. So that's going to be negative 1 over 5 minus negative 1 over 1. So negative 1 over 5 plus 1 is going to be 4/5. So my actual integral from 1 to 5 is 4/5, which is 0.8. And I'm just showing you that, you know, we're using like a smaller situation where your RRAM ended up being your lower bound because it's decreasing function. So it was your underestimate, your LRAM was your overestimate, your actual area ended up being somewhere in between. So now let's think about this, okay? Let's think about something else here. So our summation from n equals 1 to infinity, a sub n, is equal to, and our a sub n is our 1 over x squared, or 1 over n squared, is equal to 1 plus the summation from n equals 2 to infinity. But all of that is going to be less than the integral from 1 to infinity, a sub n. Because that integral is going to end up being the upper bound of the series, okay? So this integral right here is the upper bound of the series. So as we start using the integral test, I will keep referring back to that. And what we're gonna think about is if the integral converges, the series is bounded. Oops. And if the integral diverges, the series is unbounded. So when we go to see our integral test definition right here, to use this test, f must be, number 1, continuous. Number 2, it must be positive. Number 3, it has to be decreasing. And number 4, it needs to be on the interval from 1 to infinity, right? So all 4 of these things need to be true before you can even use this test. Then you will take your a sub n and you'll think of it as a function. And I change it to f of x because that's what our calculus book does. For some reason, these notes change it to f of n, but I want you to think of it as a function. So I'd like you to think of it as f of x. And look, even right here, they put f of x. So I always do f of x, but you're going to see in the notes and the answers that I'm going to post that she will be using f of n, which I don't care. I think, you might like f of n, so I'm going to leave it alone. But I just typically use f of x because I want to remember that this is my function and that I'm trying to, change that a sub n into a function. First, I have to make sure that it's continuous, positive, decreasing on the interval from 1 to infinity. Then, if it is, I can look at the integral from 1 to infinity, and if it's convergent, then my series is convergent. If my integral is divergent, then my series is divergent. Okay, so this is a nice test. It's not hard at all. So you just have to make sure that, that you understand it. And we have to check all those things. So basically, summation n equals 1 to infinity of a sub n and integral from 1 to infinity a sub n, well, I'm not even going to call it a sub n. I'm going to call it f of x dx, but your f of x is basically f of n. They either both converge or both diverge. Okay. And so now, example 2. Apply the integral test to each of the series below. And I see that they spelled integral wrong. Sorry about that. Summation n equals 1 to infinity of 1 over n squared plus 1. So I'm going to say let a sub n equal 1 over n squared plus 1. A sub n equals f of n, and I'm going to go on to say f of x. So I'm going to look at the integral from 1 to infinity of 1 over x squared plus 1. Now, was it continuous? Is my 1 over 1 squared 1 over x squared plus 1. Is there anything that gives me a vertical asymptote? No, because I'm squaring x, so I'll never get a negative 1 there. And so I don't have to worry about that. And if I looked at the first few terms, if I put a 1 in, I'm going to get a 1/2. If I put a 2 in, I'm going to get a 1/5. If I put a 3 in, I'm going to get a 1/10. So you can see it, well, we know that this is continuous. You can see that it's decreasing. So we said, number 1, it has to be continuous. Number 2, it has to be positive. Sorry. They are all positive. Number 3, it has to be decreasing, right? On 1 to infinity. And it is. You can see that this is decreasing. So we are able to use the integral test. It passes number 1, 2, 3, and 4 to allow us to use it. So now we've got an improper integral. So we do always have to change this to a limit. And I'm just going to say, as b goes to infinity, from 1 to b, and I don't know if this looks familiar to you as a derivative, but it should look familiar as the inverse tangent derivative. So we've got the limit as b goes to infinity, inverse tangent x from 1 to b. So limit as b goes to infinity, inverse tangent of b minus inverse tangent of 1. So I don't know if you remember what inverse tangent looks like, but inverse tangent, as it goes to infinity, your inverse tangent just keeps going towards pi over 2. And inverse tangent of 1 is pi over 4, right? Where is the tangent 1? Opposite over adjacent is 1 at pi over 4. So this becomes pi over 2 minus pi over 4, which is pi over 4. Okay? So since this integral is pi over 4, that means that your integral converges, right? Since f of x equals 1 over x squared plus 1 converges as if I added up all of the area between this function and the x-axis from 1 to infinity, I would get pi over 4. Okay? So therefore, summation n equals 1 to infinity of 1 over n squared plus 1 converges. So since comma, okay, and let's do B now, because your answer here was converges. And now we've got summation from n equals 1 to infinity of n over n squared plus 1. And we are going to let a sub n equal n over n squared plus 1 equal f of n equal f of x, x over x squared plus 1. You don't have to write all this out. I'm just trying to make it make sense for you. So don't worry about writing all that whatever. You could go straight to, it's telling you to use the integral test, so I know I'm going to be doing, the integral from 1 to infinity of this as a function, okay? And then limit as b goes to infinity, 1 to b, x over x squared plus 1 dx, and I'm going to let my u be x squared. My du would be 2x dx. So du divided by 2x is my dx. So limit as b goes to infinity. This is going to be the integral of x over u plus 1 times du over 2x. And if I put 1 in for x, I get 1 squared, which is also 1. If I put b in for x, I get b squared, which is b squared. So I'm changing those so that I can keep my u. So the limit as b goes to infinity, and the x's cancel. Sorry, forgot to do that. This is going to be 1/2 integral from 1 to b squared, 1 over u plus 1 du. So limit as b goes to infinity, 1/2. This is going to be ln absolute value of u plus 1 from 1 to b squared. So this is going to be 1/2 ln absolute value of b squared plus 1 minus ln absolute value of 1 plus 1. And this one, if you wanted to, you could put it as b squared plus 1 over 2, right? You could say, but either way that you write this, you could say 1/2 ln b squared plus 1 over 2, right? Either way you look at this, if I put infinity in, I'm talking about taking the natural log as you go, and you know that the natural log slowly rises, and so therefore this limit is going to be infinity. So since this diverges, then our series is going to diverge, okay, by the integral test. So we're going to say, since f of x equals x over x squared plus 1, or that integral, I guess I should be writing it as that integral diverges, right? Basically goes to infinity. So if I'm adding up all of the area between this function and the x-axis, it's going to go to infinity. And so since that function diverges, from 1 to infinity, then summation n equals 1 to infinity, n over n squared plus 1 diverges by the integral test. Okay, so our answer is diverges. Okay. Comparing two series. Let's explore why 1 over n squared converges, but 1 over n does not. Consider the following grouping of terms in the harmonic series. Show that the sum of each group of fractions in the series is more than 1/2. So you can see that that 1/2 is 1/2, right? So that works. I'm going to change colors. The next one, the 1/3 plus 1/4, that one is 7/12. And think about it, half of 12 is 6, so this has to be 7, has to be greater than 1/2. And then the next one, the 1/5 plus 1/6 plus 1/7 plus 1/8. If you put that in your calculator, you should get 533 over 840. And half of 840 is 420, and it's greater than, 533 is greater than 420, so you know that this is greater than half. And then if you added all the next one, it's going to also be greater than 1/2. So you can do that. I ran out of space there. I think it ends up being 21,635 over 36,036, but it's greater than 1/2. Now consider the terms in the series summation 1 over n squared, and group them any way you like. Yours are going to be different than mine, but I went ahead and looked at like 1/4 plus 1/9, and I got 13/36, and that is approximately 0.36, which is less than 0.65, and then 1/16 plus 1/25 plus 1/36. I went ahead and added those up. I got 469 over 3,600, which is approximately 0.13, and that is less than 0.65. So I looked at it like that and saw that, if all of these summations are less than 0.65, and I'm continuing to add smaller and smaller and smaller and smaller values, then it seems like this one would converge, right? It's not going to keep getting bigger and bigger and bigger. Like this one, if I keep adding and all these numbers are greater than 1/2, I'm going to keep adding and adding and adding, and my summation is going to keep going to infinity. So that's what we were trying to say. If it's just 1 over n, it's going to go to infinity. Your series is, the summation of all those terms is going to go to infinity, so therefore your series diverges. So the harmonic series, when it's just summation 1 over n, is always going to diverge. But if we just change one little thing and we take it 1 over n squared, that n squared is strong enough that it converges at that point. And it says for part C, explain why the harmonic series never converges. I just put that after the second term, each grouping of 2n terms will have sums greater than 1/2, which is the value of the second term. And so, you've got the value of the second term, and then you're adding it. They're just getting larger. Do you see what I'm saying? So all of these terms are greater than the value of that one, so it's just like getting larger and larger and larger and larger. That's why it's going to diverge. It will not converge, 1 over n. But if you change it just one thing, just 1 over n squared, that will converge. So that is called a p-series. So now we're going to define a p-series. A series in the form of summation n equals 1 to infinity, 1 over n to the p, is called a p-series, where p is a positive constant. For p equals 1, the series is called a harmonic series. So this p-series, if p is greater than 1, it's going to converge. If p is between 0 and 1, it diverges. And if p is equal to 1, it also diverges. So for this p-series, you can just, if you've got something as simple as this, 1 over n squared or 1 over n cubed, you can just use the p-series test. Since p is 3, 3 is greater than 1, therefore the series converges. Okay? So it truly is as simple as that. But of course they're never, they're very, quite often not this simple. But if you do get one that's this simple, you can say, oh, wait, I've got a p-series here. And I know that, since my p is whatever, then it either converges or diverges. So the first thing I would want to do on this one is I would want to simplify my n in the denominator. So this would be n to the 2 over 2 plus 1 over 2. This would be n to the 3 over 2. And I would say this is a p-series. With p equal to 3/2, which is greater than 1. Therefore, the series converges. By the p-series test. So your answer actually is converges, because it's just saying determine whether the series converges or diverges. So this one I would want to make and simplify just so I can see what that P is. 1 over n to the 1/3. This is a P series. With P equal to 1/3, comma, I mean, you could say, since P is between 0 and 1, I should put since there. Since P is between 0 and 1, the series diverges. By the P-series test. This one's going to be 1 over n to the 1/4. And it's going to be the same thing. This is a P-series with P equal to 1/4. Since P is between 0 and 1, the series diverges by the P-series test. This one, you could also use the integral test. So I'm going to do that after I finish D. I want to show you how, you don't always have to use one test or the other. Sometimes you have choices, and you want to try and use the one that's easiest. So, of course, the P-series test here would be easiest. But it may be helpful to see the integral, it solved using the integral test. And when you look at this one is not a P-series, okay? The n is not your base. So, I mean, if you wanted to rewrite this one, you could think of it as 1 over e to the n. So I flipped it, e over 1 to 1 over e, and then it became to the positive n. So now you could look at it as a geometric series if you wanted to, or you could also use the integral test. So, there you could think of it as geometric. You could think of it as trying to use the integral test. So, there's all kinds of ways to do this. Let's go ahead and use the integral test on this one. I'm just going to write integral test just to remind you. 1 over e is decreasing. It's constant from, 1 to infinity, decreasing constant. And so it is a good candidate for the integral test. So integral from 1 to infinity, I'm going to actually write this as e to the negative x. It might be easier to integrate it, dx. I could have written 1 over e to the x, whatever, but I just went straight to e to the negative x. And of course, it's an improper integral. We have to change this limit as b goes to infinity. The integral from 1 to b, e to the negative x dx, which is limit as b goes to infinity, negative e to the negative x from 1 to b would be the integral. So limit as b goes to infinity, this is going to be negative e to the negative b minus negative e to the negative 1. So we want to definitely write this a little different. This is negative 1 over e to the b. This is positive 1 over e. So if I put infinity in, this one is going to go to 0. And so my whole thing is going to go to 1 over e, right? So 0 plus 1 over e. What did we say using the integral test? Do you remember? If we get 1 over e, do you remember the integral test tells us that that is the upper bound of the summation, right? So it tells us that this, if you go back and look at integral test, we said that the integral of that function is the upper bound of our summation, right? A sub n. For, and our a sub n here would be e to the negative n. And so the integral test, since this is an actual value, that means if we took the area under the curve between that curve and the x-axis, we get 1 over e. Okay, that's the value we get. That means it converges. Okay, so since this integral actually has a value and it converges, then our series is going to converge. Okay, now since we know that this is actually a geometric series, and our first term is 1 over e, and our r is 1 over e. So summation n equals 1 to infinity, e to the negative n converges, and it also converges to the sum a over 1 minus r. So this ends up giving you, if you simplify it, 1 over e minus 1.